Thank you again for attending here this Future Leaders in Robotics and AI Celebrating Diversity and Innovation Seminar Series, again, sponsored by the Microsoft DC Metro Engineering site. Our next presenter is Dhruv Shah. He's a final year PhD candidate in electrical engineering at UC Berkeley, where he's advised by Sergey Levin. His research spans the fields of machine learning and robotics, with the goal of building autonomous robots that can combine large-scale learning with real-world deployment. Dhruv is a Berkeley fellow. His research was a finalist for the Best Systems Paper Award at RSS back in 2022. His work is also being featured in several media outlets, including IEEE Spectrum, Tech Explorer, 2Minute Papers, and ZDNet, along with several international venues. And so with that, I'll stop sharing and let Dhruv take it away.
All right, thanks, Yancy. Can you see my screen? Robots moving?
Yes.
Perfect. All right, thank you so much for the invitation, and thanks everyone for joining. Alina gave us a lot of insights kind of on the algorithmic side. I'm going to switch gears a little bit and talk about data-driven methods, big models, things that might not be the best idea when you're thinking about edge deployment, but still lots of exciting opportunities for us. So as a quick overview, my research goal is to enable intelligent autonomy for robots in a variety of environments and applications, ranging from assistive home and office robots to robots doing autonomous inspection, safety checks, search and rescue, and so on. This is particularly exciting for me because it forces me to think about challenges and opportunities in building robots outside of simulated home and office environments, and really think hard about how we can build algorithms and methods that work for any robot in any scenario, even if the environment is unstructured. Data-driven methods today, as a lot of you might be aware, they've been very effective in the last decade. We can autonomously perform very complex tasks like folding clothes, navigating tight hallways while avoiding collisions, control quadrupeds that can do interesting tasks. But if we really look under the hood, under their operations, they face some fundamental limitations that prevent them from being deployed in open world scenarios, either because they make strong assumptions about the structure of their environment, or they require trial and error data collection that can be expensive, unsafe, or maybe just infeasible for a lot of applications. And they fail to account for a good semantic understanding of their surroundings, such as these stairs being a bad idea for a robot of this size, where it trips and then it has nothing it can do. Due to these limitations, data-driven robotics approaches are limited to simple, restricted settings and are not particularly accessible to a majority of practitioners and potential applications. What I want instead is something that looks a lot simpler. And you could say this is a dream and we might never get there. Let's say you're a practitioner, you order a new robot from Amazon, or perhaps robot parts from a favorite hobby shop. You assemble it. You go online, you download an intelligent robot brain, your favorite algorithm from GitHub. And then out of the box, the robot starts showing intelligent behavior. It starts acting in a reasonable and useful manner. This is quite a ways off from where we are today. So for inspiration on how we might get there, let's take a look at how our neighbors in computer vision and NLP have dealt with some of these challenges recently. Over the last few years, we now have some excellent general machine learning models for scene understanding, helpful chatbots that can answer general questions, or even very specific diagnoses like medical diagnosis, understand images and answer complicated, tricky questions about them, or even generate high-quality images and videos. All of these models, as I'm sure many of you have interacted with them, they're able to solve these challenging problems and interact with millions of users around the world, all of which have different preferences, different styles of interaction, and yet they seem to work quite robustly for all of us. If we can reciprocate this kind of performance and generality in robotics, it might open a whole avenue of new applications for robots of the future. The secret sauce, as it stands, is data. All of these machine learning models were trained on a large amount of diverse data across multiple different tasks, and they learn to start identifying some of these underlying patterns in the data that make them extremely robust and versatile for downstream applications. This class of neural networks, often called foundation models, refer to models that are trained on broad data sets across multiple different tasks, generally using unsupervised or self-supervised learning approaches, and they've shown some very great zero-shot generalization capabilities, as well as the flexibility to be used downstream. In particular, I'm going to call these models Internet Foundation models, since they are trained on vast amounts of text, image, and video data that's commonly found on the internet. I believe that a similar consolidation of models and objectives will be a transformational paradigm in data-driven robotics. And while scaling alone is not going to be sufficient to solve robotics, there's a lot of useful things to be gained by taking this data-centric perspective. At the core of these internet foundation models is collecting and leveraging large amounts of rich and diverse data. Unfortunately, this is at crossroads with the fundamental challenge in data-driven robotics, which is that collecting robot data is expensive. So my research was focused on enabling data-driven methods by leveraging existing sources of data across several different robotic embodiments that people already have lying around. And while all of this data looks quite different, I've shown that by defining the right objective and architectures, we can use all of it to learn transferable representations that are useful and can be deployed across all of these different robots. Since you're no longer bounded by data that you can collect on your own system, you can now arbitrarily scale up the amount and complexity of your data, which makes it a very unique opportunity in machine learning. And to go beyond understanding what can be collected by robot data itself, I've also explored how we can use existing foundation models of text, vision, and videos, which have shown some phenomenal text-based reasoning and visual grounding capabilities. On the path to building open-world robots that actually work, I've looked at what it means to have a foundation model for robotics, where we might get the data, how we might train this model to control multiple different robots, and inspired by recent progresses in foundation models of vision and language, my research has studied how we can build this pre-trained backbone for robotics and adapt it for downstream tasks. I've also looked at how we can augment these robot models with the very nice capabilities of today's internet foundation models that are excellent at parsing human instructions, performing simple high-level reasoning, as well as image-level semantic understanding. In the interest of a focused discussion today, I'll primarily be focusing on this foundation model piece, which is designing, training, and fine-tuning a robotic model, and what I like to think of as a cross-embodiment hypothesis. Towards the end, if we have some time, which I doubt we will today, I can try to contextualize this in the bigger picture. In particular, I will use the visual navigation subproblem to instantiate the challenges and design of such a model. Navigation is a particularly well-suited task because there already exist a large number of readily available data sets and platforms that people use today, and a lot of applications that can be useful. I might also kind of touch on how some of these ideas apply to problems beyond the navigation subproblem, including preliminary results in manipulation and mobile manipulation. All right, so let's get into it. Before I go any further, I want to take this moment to define what I mean by a robot foundation model. It's a fairly overloaded phrase, especially if you use Twitter or X these days, so I'll try to be concrete in my version of it. I want to define a robot foundation model as a model that, once trained, and hopefully it is trained with little to no external supervision, it can be deployed zero-shot to a variety of completely different useful settings. This would mean completely different robots with different sensors in new environments, around new kinds of people, and so on. And it can be adapted to a downstream task of choice, which could mean different objectives, different kinds of behaviors, different ways of specifying the task, and so on. And ideally, all of this would be something open source that people can readily download from Hugging Face or GitHub and test on their robots right away. The key thesis for training this robot foundation model is that we can train effective control policy across robotic embodiments and tasks. Beyond going beyond the current paradigm of collecting small singular data sets and training end-to-end policies for each specific robot and each specific task, I want to think about how we can leverage the shared structure across all of these data sets. So first, we'll combine all of these different data sets and curate this heterogeneous data set across the robots. And then we'll figure out a way we can train a giant machine learning model, which I'm going to call the robot foundation model, across these data sets and tasks. So let's say you have, in robotics, let's say you have a data set of trajectories tau, where for each time step t, you have images or any other form of observation modality, which is shown by the blue squares, and then actions taken by the robot when the data was collected by the action labels at the bottom. What we can do is we can sample start and goal states in this trajectory, which in this case would be start and goal observations or images, and mask out a few things from the data set. We'll mask out at the top the time steps corresponding to these observations, and also a set of future actions that the robot took beginning at the start state. This would allow us to set up a machine learning problem with a masked pre-training objective. Given the start and goal observations, our neural network must learn to predict the two masked out quantities. The first corresponds to the difference in time steps between the start and the goal, which is known as the temporal distance to the goal. Alternatively, you can think of this as a value function. And second, a fixed horizon of future actions that the robot can take to make progress towards the goal. If you kind of really want to squint and look at the bigger picture, this is very similar to how a lot of visual and language pre-training depends on these mass training objectives, where you use existing data sets without generating new labels and try to curate interesting representation learning problems. So we'll take these two targets and train them with goal-conditioned behavior cloning, which is to say that the neural network model will be trained so it can repeat behaviors similar to the ones contained in the dataset. And while this may sound suboptimal if the data was not collected with an expert policy, the interesting fact here is that we'll train this policy to reach short horizon goals. This will be used as a short-range policy, and we can show that behavior cloning can learn near optimal policies for short-range goals. And then for reaching faraway goals, we can combine this policy with a high-level planner or some other mechanism. I won't get into the details of the planning and memory, but if anyone has questions, I'm happy to take them at the end. To facilitate training this neural network model, I pioneered the first effort to aggregate heterogeneous data sources collected by different research labs across the country and across different robots, and standardize practices for cross-embodiment robot learning. As you can tell by looking at these robots, they have widely different capabilities, speeds, and also action spaces. For instance, the Roomba at the top moves at a few centimeters per second and usually indoors, whereas an ATV at the bottom right moves about 100 times faster when it's zipping through a forest, uses Ackermann steering, which is a very different controller, and we'll have to figure out how to best learn from this kind of data by using clever architecture design. As an artifact of this initiative, we open sourced about 150 hours of visual navigation data, which is an order of magnitude larger than any existing navigation dataset. And this has been widely used by the community since its release for research not only on robotic navigation, but also active perception, out-of-distribution robustness, and video modeling. So going back to the schematic, for cross-embodiment learning, we want to go from these n different robot data sets and individual end-to-end policies to a regime where, now that we have this data set that is combined across the different models, we want to have a giant model. The first modeling decision we'll make is, rather than making model predictions in each robot's low-level action space, we make the predictions in an abstract action space that can be shared across the robots. Most simply, this could look something like future waypoints or 2D waypoints for navigation robots, or 3D or 6D end effector position for manipulation robots. And for each robot, we can have a separate translator function, which could be a neural network or not, that can convert these abstract actions into low-level actions. To allow making predictions that can be conditioned on the robot's capabilities, we'll also condition the model on a robot-specific context or prompt, much like how language models are conditioned on prompts to provide different behaviors. I'll now describe these two components in slightly more detail. So where we left off, we have this neural network policy. Notice that the units of distance, which is already a temporal distance, units of time, they're in some way independent of the robot scale. But if you look at the action units, if they are raw actions, then they can be really hard to model because our robots can have arbitrary speeds, different scales, and so on. So as I alluded to earlier, we'll make a change by defining a unified abstraction, which in this case could be a sequence of future waypoints. The second change to make this work would be to eventually figure out how do you map these abstract actions or waypoints to something that's something that the robot can actually understand. And for each individual robot, this would look like a robot-specific translator function, which will convert this action space into each robot's low-level action space. This could be something as simple as a classical controller that is used for tracking waypoints using PID, or a model-based or a learned neural network controller that we use for something like our quadrupeds. This gives us a mechanism to simplify the machine learning problem by standardizing the outputs while we still control different robots. That leaves us with the other challenge. If you look at videos of these 3 different robots in different scenarios, their behaviors are indeed quite different. The Go one is quite agile. It can turn in place, whereas the Jackal typically drives faster and makes wide turns and so on. So we need to figure out a way where we can condition the model on the robot's capabilities or its identity so it can elicit specific kind of behaviors that make sense. I won't go too much into the implementation details, but roughly we can do something really, really simple. We can condition the model on a past history of the robot's observations, and the hypothesis is that this history can be predictive of the robot's capabilities. So intuitively, if the camera is fixed at a certain height above the ground and your observation history shows that you're moving slowly around a couch, that may probably indicate that the model is driving a slow indoor robot, and that would prompt the model so that the output trajectories are also compliant. This manner of conditioning the model on the robot's past observations is akin to prompting autoregressive language models to elicit specific behaviors. So concretely, as I motivated, we'll have start and goal observations, as well as a fixed number of frames corresponding to the embodiment prompt to condition the model's capabilities. And we can then process these frames individually using convolutional encoders, shown here as efficient nets, but you can use your favorite ResNets or vision transformers. We'll then take these visual tokens, which are fixed dimensional vectors, and process them using multi-headed attention layers formed by a transformer decoder. Lastly, we'll pool the output of the transformer block to obtain a context vector, which will be used to make the final target predictions. For the temporal distance, we can use a very small, fully connected neural network that can predict a single scalar corresponding to the distance. For the actions, we need to do something a little more expressive to model the diverse behaviors that robots can express in a lot of these scenarios. Most robotic tasks are inherently multimodal, and we find that using a very expressive policy class like a diffusion policy really helps. Putting it all together, we get an architecture that looks something like this. Processing a string of current and past observations and predicting temporal distance and future actions, which is akin to predicting a value function in a policy. As it turns out, these are the very same building blocks that have led to successes in language, image, and video modeling communities, and they work quite well for modeling robotic trajectories as well. This gives us a very scalable architecture that can easily range from 5 to 500 million parameters and beyond, without changing the fundamental structure and inductive biases imposed by the model. And all of this put together allows our single neural network policy running on many different robots in many different environments. Here I'm showing 4 examples where the same model, without any additional data collection, without any fine-tuning, and with different sensors, different cameras, different robots across California, Georgia, all over the place. We have these robots crawling around, solving tasks in the real world, and behaving differently, like avoiding collisions, behaving safely around humans, and so on. Looking at one of them in more detail, here's a video with a live robot demo that we did at Coral late last year in Atlanta. We wanted to throw ourselves a challenge, so we went to Georgia Tech without a robot. We borrowed a robot from Georgia Tech. We strapped on a GPU on its back, downloaded some code that we had already released a few months ago. And here's an example of the demo that ran for 3 days, where people would come to the robot, give it a task, which would usually mean something like going to the other end of the conference center or walking around an obstacle in the middle and reaching the goal. And yeah, the robots look really well. Something I really want to point out is none of our training data sets actually had humans around them. So this environment is so out of distribution that none of us had any hope that this would work. But somehow the learned policies kind of realize that humans are kind of like trees, and driving between humans might just be like driving between trees and avoiding them. I'll fully acknowledge that that's not ideal. And the robot is not doing anything smart. It's not actually perceiving human intent or behaving in an intelligent manner. But it is really cool to have policies that are so robust that they can work out of the box in a lot of these challenging scenarios. Perhaps the real strengths of a quote-unquote foundation model, as I tried to call them, is how they can serve as a starting point, a foundation for more interesting things that you can build on top of them. And I want to share a few exciting projects that I've worked on using these RFMs as a base model in different ways. First, we explored how we can start from a base RFM, which, as I mentioned, very honestly, it was only trained to do standard goal reaching. It does not care about humans. It does not care about multiple agents. But we figured out that if all you want to do is learn better, more socially compliant navigation behavior, it is a good idea to start with a backbone that is already robust. So in this case, we trained a separate pedestrian trajectory forecasting model and used it as a reward model to iteratively optimize the RFM to perform navigation while minimizing occlusiveness to humans around it. If you caught the first half of the series, it's very closely related to how model-based RL works, but we did this in a very supervised fine-tuning fashion. In another project, I explored how we can adapt a pre-trained model, which was only trained to reach image goals, to now reach new different kinds of goals, such as text commands or GPS positions. Something very nice about using a thing like a transformer is that all the pieces are very modular. So a very simple case, you would get rid of the part of your model that attends to the goal, you would replace it with a different kind of goal. You would freeze the rest of your model. So now 98% of the parameters of your model are completely frozen. And then you would fine tune it with a very small amount of data to now teach an old model new tricks, where you can now teach it to obey different kinds of commands, but do this in a very efficient way. Lastly, we also found that RFM training leads to inherently better visual representations for robotics compared to just doing visual pre-training. So notice how state-of-the-art visual pre-training methods based on supervised or unsupervised objectives fail to really solve any task satisfactorily, and it barely outperforms the training the entire policy from scratch. I'm intentionally leaving out a lot of the details, but just assume this is an experiment with some sane evaluation done. Instead, what we find is when you're trying to train representations that were trained with robotics tasks in mind, they transfer significantly better, suggesting that a robot-specific pre-training paradigm has a lot of benefits over pure visual pre-training that you can get from ImageNet or masked autoencoders. This is very closely related to Gibson's hypothesis of tight coupling between action and perception, which has been studied in many different settings over the years. And beyond showing results on multiple different robots, an aspect of robot foundation models that really inspires me is that it gets us closer to this vision of plug-and-play robots that I opened my talk with. In the last year and a half or so, since we released these models and checkpoints corresponding to these papers, there's been a phenomenal response in the community, with 25 or so different researchers and labs that have deployed and adapted these models for a lot of downstream applications. And I want to show you a few examples of what the community has been doing with these models. On the top right is a paper from Finland that uses the same model that I showed all of these videos of, a zero shot. They downloaded from GitHub, no fine-tuning, no data collection, and they use it as a low-level policy for their visual face recognition research, where this model is now driving around a campus in Finland and hopefully not colliding too much and avoiding water only sometimes. On the bottom right is one of our favorite videos of a research group in Estonia that used my model as a base model. They collected some data, they fine-tuned it for their task, and then participated in a human versus robot orienteering competition, which is kind of a treasure hunt style thing. I didn't fully follow how it went, but I think the robots lost really, really badly. But we were the best robot, so I still count that as a win. And lastly, here's a video I really like from Princeton, where researchers use my RFM out of the box as a baseline for comparing their vision-based control policies. They beat our baseline, which is fine. It was a good paper. But this is particularly exciting because reproducibility of results has always been a fundamental challenge in both robotics and machine learning. Since we all use bespoke hardwares, we only test in our own labs, there's no very standard evaluation practices. And I'm very excited that going towards a direction where we can publicly release our models and they work in any scenario on any robot gets us closer to removing some of these barriers in accessibility and reproducibility. And lastly, the same idea of doing cross-embodiment learning from navigation has led to a much larger effort in studying what this looks like in a task like tabletop manipulation, which has a lot more researchers working on it. This led to a large collaboration across 34 research labs, and we just found out this morning that it's been nominated for 3 awards at ICRA, which is very exciting. If I'm going to see people at Japan, it's going to be great. But yeah, another artifact of this research has been there's been over 1,000 hours of robotic manipulation data that is now public. If any of you are interested, shoot me an email. We can figure out ways where you can use this data set, but also you can contribute your own data and be a part of this growing community of people that want to work with real robots and are not scared when things break. It's okay, things break. Right, so I'm going to wrap up now. As a quick summary, I talked about how we can train a cross-embodiment robot foundation model that can control many different robots in zero shot and be adapted to a variety of downstream applications and objectives. I also discussed how these RFMs can be combined with internet foundation models. Well, actually, I kind of did not discuss it. This is a stale takeaway side, but trust me, and you can ask me questions about it. But we can, I will have discussed how we can combine this with some other ways to kind of combine everything together. I don't have too much time to kind of go into the broader vision, but let's all work together towards this picture where we can have giant models that work on all robots and deploy in all sorts of scenarios. And I'm really excited kind of for what this means, both in terms of advancing the field of robot learning for building better models, but also how this adapts to how this aligns with other communities, thinking about algorithms and methods for doing continual learning, with reinforcement learning, and applications eventually that extend into the field rather than sticking into our labs. Before I finish, I want to thank all of my mentors, collaborators, and funding agencies that played an integral role in enabling the research that I presented in this talk. And I'm happy to take any questions about my topic.
Thank you again. The wonderful presentation, very, very enjoyable. I'll open it up to the audience. Are there any questions for the speaker? If you do, please use the Q&A feature to post your questions. I do have a couple of questions that I can start with while we wait.
Go for it.
The first one is, so obviously, we're using a traditional motion planner and we have a lot of information. We can, outperform, right, the performance of this. And so the advantage of this foundational model, right, is a generalizable zero shot, right? But how does the performance compare, right? So, are we gaining, different magnitudes of performance improvement by going motion planner, or is it comparable? What do you think?
No, that's an excellent question, and I think in some ways it is complementary. So I think a good mental model to think about what are we gaining by taking this data-centric perspective is it really helps us to work when you're reasoning in very high dimensional spaces. So if you're thinking about motion planning, but when you don't have a structured representation, I think if you do have access to a very nice structured representation, whether it's a 2D occupancy grid, whether it's a 3D voxel grid, it's really easy to do motion planning. If you have very partially observed spaces, it's hard. And what helps is there's been a lot of exciting work in learning-based motion planners, which nothing to do with everything I talked about today, but in some ways, kind of the angle of learning-based motion planning is you don't always need access to this very highly observable spaces, and you can still use some of these nice data-driven cues that help you there. Everything I talked about today, I think it is particularly hard to do very fair comparisons, because if I define the task as you want to go from images to actions, it's hard to go to a representation where you can do motion planning. Philosophically, I think if we want to break this down into a perception, planning, and control kind of hierarchy, I think everything I talked about today is kind of part perception, part control. And the part I intentionally skipped is the part where you do planning. I am a big believer in doing explicit planning and then figuring out how you get your planners and controllers to speak to each other. So I think we're a few ways away from something that is clean and has good analytical understanding. But I think the direction where this is going will hopefully eventually kind of merge everything into something that's a lot easier to answer a few years from now.
Absolutely. Questions from the audience?
I have a question. There is one. Go ahead.
We have from Chahad Deep Sea. So the VINT requires of goals or goal image. How do you plan to navigate for exploration tasks where we need relationship between explored and can be explored?
Great question. Yeah. And wow, that's a more detailed question than I even presented. So I'm glad you've thought about this. So one of the subtle details that went into the architecture that I showed you is when you're trying to figure out the best way to use existing data sets, we made an interesting choice, which is weird. We're conditioning policies on the goal image itself. And a natural shortcoming here is if you've not been in an environment before, you don't know what a reachable goal image looks like, which means if you go to a new environment, what are you going to do? We've done some follow-up work, which I did not kind of go too much detail, but the paper that's linked second on the slide, Nomad, we figured out a way where the goal image conditioning is just optional. So it's a good way to structure your search, the training problem. But if you are exploring, you would remove the goal image. You would not specify any goal information, and the model would just look at the observation and predict a set of useful actions it can take. The connection here between this notion of exploration and sampling-based motion planning is that this model would actually be your sampler. So an interesting design decision here again is you have this diffusion policy, which lets you sample multiple candidates. So in the very specific way you're thinking, the way you would use this model for exploration would be you take this model, you don't give it any goal, you put it in an environment, you use it to sample actions, and in a data-driven way, it's not certifiably safe, but because it's trained on good data, it's empirically going to hopefully give you a set of intelligent exploration candidates that do not run into walls and do not hit people. And then you can have a light planner that might be on top of this that would score these trajectories perhaps, and then let you pick what you do. And that is exactly what we do. So a lot of the exploration results, which I did not present in this talk, the way we conduct them is you have a sampling-based planner on top that uses this model as the sampler. And this would kind of get rid of things like having a collision checker in some ways. Follow-up question, do you have access to traversability, specifically in case of exploration? No. The only observations you have from the environment are visual, which kind of makes this a little bit harder than it needs to be to get a principal solution. But no, you have no traversability estimates. And in some ways, the model kind of bypasses traversability and directly gives you trajectories or paths that you can sample. And hopefully they are traversable paths. And yeah, maybe that answers the question.
Thank you. We have time for a quick question. I think Elena had a question.
I was actually going to ask about the exploration question, so it was covered.
Right, fantastic.
Okay, awesome.
Yeah, great.
I mean, yeah, even if they don't come up now, I'm happy to answer any questions. Just shoot me an email. Which reminds me, I should have put my email somewhere here. Yeah, just shoot me an email. I'm sure you'll find the email. Yeah.
Absolutely. So in the interest of time, I'm going to, again, thank the speakers for presenting and thank the audience for attending. We do have more seminars coming up, including next Friday. So we hope to see you all. I'm going to terminate the recording, but feel free to stick around and ask your questions if the speakers have time. And, I'm sure they'll be glad to stick around. Thanks again for attending. Hope to see you soon.